Okay, thank you. So I'm Michal Šturc. I'm PhD student at the Department of Astronomy. And the theme of my thesis is gravity on large scales and dark matter. Mostly not dark matter yet. We are trying to find a modified version of Newtonian gravity that would explain the discrepancy between rotation curves, observed rotation curves, and the measured, calculated rotation curves from the baryonic matter. Mostly everybody here has already seen such a picture that the calculated values for orbital velocities of stars in galaxies are actually much higher than what baryonic matter would hold together. So the options to explain this phenomenon are either to add some matter, which Zwicky did in the 1930s, change the second Newton's law, which Milgrom did in 1980s, or to change the gravity law, which McGurk proposed in 2010s. I think that this approach failed because there were some insurmountable problems. So the adding of dark matter is the scientific mainstream at this point, and this is a little bit different. I don't have too many equations here because I'm saving them for the department colloquium. Okay, so what do we mean by large scales? By large scales, we mean distances from massive objects where the gravitational acceleration is less than this value, and the same exact value, modulo some uncertainties, is the same for Milgrom's Mond and the McGurk's modified gravity. These distances for the Sun are roughly 7,000 astronomical units, so roughly the distance where comets, long periodic comets fly. For the Milky Way, it's roughly 30,000 light years, so more or less the region where the Sun is. And for large planets such as Jupiter, it's 200 astronomical units, so far beyond Pluto and basically the Kuiper belt, or whatever it's called. And this obviously presents massive problems for any sort of experiments because the furthest we have reached with the probe is like, how much is that? 50 astronomical units, so roughly 1/4 of the, the Jupiter value is not really relevant, but it's like 1% of this. So this means that we are stuck with astronomical observation of either stars or galaxies, or maybe not, because we can find points and areas with low gravity even in our solar system. If we have two massive objects, we can always find a point with zero gravity between them. This is given by the intermediate value theorem. If we check at if those two objects are on the x-axis, then at the boundary of the first object, the x component of the gravitational acceleration is less than zero, and the x on the boundary of the second object, the x component of the gravitational acceleration is larger than zero, which means that somewhere in the middle we have a point with zero gravity. And around that point we have a small interval where the magnitude of the acceleration is less than the 10 to the minus 10. Okay, for the planets in the solar system, I included Ceres and Pluto because why not? The distances from the Sun, where this point with zero gravity lies, are, you can see that for small objects such as Mercury or Ceres, it's basically at the boundary of the planet to 4 significant digits. But for larger planets such as the Earth or Venus, it's actually somewhere in the space, but very close, still very close to the planet. And for larger planets, namely Jupiter, it's actually like 0.2 of astronomical units, which is quite significant. The more important is the length of the interval where gravity is still low. This is in astronomical units and this is in meters, so don't be confused. For the Earth, it's around 2.6 meters, and the point moves around the Sun with the same velocity as the Earth, which is some 30 kilometers per second, which would be quite difficult to get to that point and stay in that point. So I have picked Neptune as, okay, I will later pick Neptune. We can see that this is well reachable with a probe, and the interval that's interesting for us is some 280 kilometers, and Neptune moves quite slowly on its orbit, so we can even stay in this point, in this area for some time. And the closest such a point is obviously the Earth-Moon system, but it's only 62 centimeters large, and the Moon moves like 1 kilometer per second, so it's not really reachable by any measures. Alright, this is a very rough approximation where I took all the planets to be on circular trajectories, and they are not influencing each other. But this can be solved with Poincare-Miranda theorem, which is intermediate value theorem just generalized for multiple dimensions. And it works like, if we have this is a two-dimensional example. If we have a function that's 0 along y-axis at some point, and less than 0 along one axis parallel to the y-axis, and larger than 0 on another perpendicular axis, we can always see that somewhere between the x component of the function is always 0, because in all these lines parallel to the x-axis, we can use intermediate value theorem. And because the function f is assumed to be well behaved, as mathematicians say, we can assume that this will be continuous. The same logic can be used in the y direction, and since we have a continuous function that connects these upper and lower sides, and a continuous function that joins the left hand and right hand sides, it's obvious that they will intersect in at least one point where the both components of the function will be 0, and in that case even the magnitude of the function will be 0, and somewhere around that function the magnitude of the function will still be small, with some understanding of what small is for us. In 3 dimensions it works very much the same, except we have to start with a plane. If we want to have the x component 0, it will be 0 along an entire plane in the 3-dimensional space. In a very similar manner, the y component will be 0 along a plane in this direction, and the z component will be 0 along, y component will be 0. Well, I mean, you can see it, right? That it's quite simple, it just needs to be nicely drawn, and maybe I'll do some proper mathematical proof in the future, or just copy it from somewhere. This is like 2 centuries old. And in general, the first 2 planes will give us intersection, which is a curve, and then the curve will intersect the last plane in one point. And we can get some degenerate cases, such as the 2 planes will not intersect in one curve, but they will lie in each other, so there will be larger intersection. But that's generally not a problem for us. We want at least one such a significant point, so if we get more of them, it's fine. Alright, now for finding these points, we have seen that it can be quite difficult, because the area is relatively small on astronomical scales. So we need to somehow constrain the entire scope of the solar system into something that's manageable. And we need, once we find, it's trivial that the largest cube we can take is the whole solar system. The problem is that it's too large, and if we want to cut it into tiny cubes with a side of 300 kilometers, that's not manageable by, it might be manageable by some supercomputers, but I don't have a supercomputer. So we need to constrain ourselves a little bit. And what we do is that if we neglect all the planets, we'll get some point x0 between the Sun and Neptune. If we put all the planets on the same side, on one line, it will de facto make the sun a little heavier, and it will move and we will find another point x1 where the gravity is 0. And it's quite obvious from the geometry of the system that the x1 is upper estimate for the x component of this point. It can never be further away from the sun because there's just no more mass we can add to this side of the system. Then we can do a similar thing for in the y direction or z direction. The system basically exhibits some sort of cylindrical symmetry. And after some calc where we basically put all the planets on somewhere in the y direction where their y component of gravitational acceleration will be maximized, which also is not really a physical configuration because those planets have their planes of orbit have some angles between them, but still we can get an upper estimate of this length, and it turns out that the this y component is twice as much as this x component. It can be seen somewhere from the Taylor expansion of all those gravitational laws, but that's basically a technical detail. But what's good is that the point of 0 gravity can never be above this point, and never be further right from this point, and never be further left from this point. Which means that we have just constrained the point of 0 gravity to a cube of some 12,000 kilometers aside, which is, by the way, less than the volume of Neptune. And this is actually what we were aiming for, because this cube is relatively small with respect to the size of the low gravity area, or low gravity volume, or the volume we are looking for. We can cut this cube we have just found into some 10,000 part, give or take. Like, even if it's 50,000, it's still manageable by that computer. If we wanted to do the whole solar system, just on the x-axis, it's 10 to the power of 7. And okay, this can be trivially made smaller, but it's still quite a lot. And this is basically the smallest cube we can reasonably find. I mean, maybe there's a complicated way to shrink it even more, but I think we have just, I think this is fine for the preliminary calculations. And because finding the point of 0 gravity and its area where the gravity is still low is doable in relatively short time, we can do this in multiple time. We can do a time evolution of this point because it will obviously orbit the sun with its planet. Okay, so what I will do next, because this will probably be part of my dissertation thesis, so it's never actually done until they take it away from me. Check other large bodies, namely, I think the moons of Neptune will have to be considered, which is basically Triton, the rest is very small. Maybe check other trans-Neptune objects, like they are roughly the same size of Pluto. The effect of Pluto at that point should be relatively small, but the obvious problem is that we are looking for places with very small gravity, so we are comparing two small numbers, and that can't be done out of hand. We need to actually calculate it. To my best knowledge, we don't need to look at the influence of stars, because they are like 3 orders of magnitude below the scale acceleration I shown, and they are more or less spherically distributed around the sun, so they should cancel each other out, but well, better check. Plus there's the effect of the whole gravity, which is basically at the point which is roughly at the scale acceleration. And then when I will be finally sure that I have the right point for one point in time, I'll do a time evolution of this system and see how the point moves around the sun and how the area of low gravity expands and shrinks as the planets change their configuration. And hopefully I'll make a better visualization than the paint you have seen. And that's all for me. Thank you for your attention.